I'm going to talk about, I kind of divide it up into 3 parts. We'll dig in part 1 just on what do we mean by clumped isotopes. The most common application right now is for thermometry. I'll briefly mention a few other things when we talk about other applications. But what I want to dig into is the mechanics of how clumping works, why you might use it for a thermometer. And to convince you all, because I hear a lot of things in the course of when I say I work on clumped isotope thermometry, and people, very smart people, will often come in and be like, oh, that's like, I've heard black magic, voodoo, and a number of other things that suggest that there's this mystery to clumped isotope thermometry that sometimes people think that we're like, oh, that's too complicated. And what I want to convince you of is you already have the baseline knowledge, the baseline sort of conceptual understanding of fractionation and why it happens and why it might be temperature dependent. So you have all the mechanics you need, all the understanding you need to actually understand clumped isotopes already. So if you accept that framework, clumped isotope thermometry is just another equilibrium isotope exchange thermometer, like all the other ones we've used before, thinking about single isotope substitutions. It's just harder to measure. So that's what I'll be spending kind of part 1 talking about, and then I will spend part 2 digging into the sort of systems that I'm most interested in using and applying in the geologic record. So talking about, in particular, terrestrial carbonates, because I think for me, this tool, as Turi said, the way it's changed my life is it's opened up a lot of avenues for exploring terrestrial paleoclimate reconstruction that have been really hard. They haven't become less hard. They've just, certain problems are more tractable than they were. And then part 3, as we have time, I want to make sure we spend plenty of time on parts 1 and 2. I will actually talk about some of my current research in these geologic questions so you can kind of see the lessons we're learning from terrestrial carbonate formation and from using this tool. How does that manifest itself geologically when we try and interpret some of these records in the past? Okay. So you've already been introduced to the concept of isotopologues, and I am guilty of having not paid attention to my color schemes and have probably hit both red-green colorblind people and blue-green colorblind people, so I've checked all the colorblind boxes. But essentially what you're seeing here are carbonate ions, where you have what we're more used to thinking about on the left-hand side, where our carbon isotope has 1 extra neutron, and so it's a carbon-13. So that's an isotopologue with 1 single heavy isotope substituted into it. And that's kind of where we've been used to occupying our space and what we've been used to measuring in terms of, say, a CO2 molecule derived from that carbonate ion, say, like what you've been doing on the gas bench with your carbonates. On the right-hand side, you see that we also have an O18 isotope. So this one has 2 extra neutrons in its nucleus, making it a heavy and more rare oxygen 18 as opposed to oxygen 16. And this is what we mean by clumping. So here we're looking at a carbonate ion that has sort of a bond between, has 2 heavy isotopes substituted in and a bond between those 2 heavy isotopes. And it's essentially this clumping, this preference for getting 2 heavy isotopes to substitute in and bond with each other that makes up the thermometer. Okay, and so we've talked about, you saw some of these with Naomi's lecture before. Again, this is just giving you some sense for abundances of these things. You've seen all of this before. Here we have our most common mass of CO2, mass 44. We have our 45 with a C13 involved. We have the most common version of 46, which has an oxygen 18 involved. And we measure all of those things. We can measure all those things concurrently on a mass spectrometer. And if we modify our mass spectrometer a little bit to add a few more of those Faraday cups, add a couple of extra detectors, we can also measure mass 47. And in this case, the most common mass, though still not very common, of mass 47 is when you have one of these C13 and O18 sort of clumped groupings. Okay, so this is just, and as we've said, there are a lot of other different kinds of isotopologues. We do try to concern ourselves with the most abundant ones, right? They're the easiest to measure. This is still, of your options, not very abundant, but you can conceive once you start to see this framework that if you could just measure it, All of these other molecules have bits and pieces of either thermodynamic information, biologic information, all the normal things that we think of involving mass-dependent fractionations are probably recorded in these isotopologues if we could measure them. And that's really where kind of this field of both of thinking about clumped isotope geochemistry, but if we want to make that more general, sort of this frontier of multi-substitution isotopologue geochemistry is really concerning itself with. Okay, so the first application of this was really focused on creating a thermometer you could use in the geologic record. So like many before, Urey and Epstein and some of the 4 founders in here, they went after carbonates. Carbonates are ubiquitous, fairly ubiquitous in the rock record. You can find them in a lot of different settings on land and in the ocean. And they contain a wealth of different information, as we've already talked about. They've got carbon, they've got oxygen. There's also folks going after calcium isotopes, magnesium isotopes, and the various kinds of things that might substitute in. So there's lots of information. And in that original thermometer, they sort of exploited the concept of equilibrium isotope exchange reactions. So I usually start this conversation by saying, okay, we'll kind of take ourselves back to Chem 101 and just think about general chemical equilibrium, right? And so finding that equilibrium point, your KEQ of a reaction, is often strongly temperature dependent. So if we kind of review our framework of that, we think about more disordered states at higher temperatures, so gaseous phases, more ordered states at lower temperatures, kind of more moving to from gas to more ordered as liquid to more ordered as solid. And we can think about the same thing when we think about equilibrium isotope exchange reactions. And so we'll dig a little bit into this. So that, a basic issue which you've probably already heard about, and repetition is always good, is that molecules behave like springs, sort of, and they all vibrate, right? And depending on which isotopes you might have plugged in, they may vibrate differently. So if we were going to look at this sort of thinking about classical mechanics, sort of physical framework, you've seen these before. We have our basic energy equation for that spring or that sort of simple harmonic oscillator, as you've probably heard before. And if you have a bond, you have some set interatomic distance. If you compress it, you kind of move up the energy well, you give it some potential energy. If you stretch it out from its happy sort of central place, you also kind of give yourself potential energy. And when we think, just like with with thermodynamics and chemical equilibrium, we're sort of striving towards our lowest energy state. Okay, so the challenge with sort of thinking about how isotopes fit into this story is that there's no real room here for isotopic exchange, for thermodynamics to sort of operate, right? Because you're dealing with all the same chemistry. So you can think about, when we think about these energy wells, kind of having this continuous range of energy levels within here that you can move between. So where we get our isotopic fractionation and this possibility for isotopic sorting based on our mass differences is when we actually think about this scheme with respect to more of a quantum mechanical perspective. So instead of a classical situation where you can have continuous energy states anywhere from the bottom all the way up until your bond breaks, up until you hit that dissociation energy, here in quantum mechanics you can only exist in certain energy states. So right, that's your N0, N1, N2, N3. And N0 is a special state, right? That's like if you could get down to absolute zero, you take all the possible, reduce all the energy as much as you possibly can, even at, say, absolute zero, where in a classical mode you'd be sitting at the bottom of the energy well, your molecule still has some little tiny bit of vibrational energy. Teensy tiny, but it's there. And that's, for us, that's why we're all in this room, right? Okay, so if we look at that scheme and we think about our vibrational energies in terms of what the mass differences do here, we can tell that we're going to end up, I always like to use sort of a slinky and balloon versus barbell mode, right? If you envision these two ends as little helium-filled party balloons, and you attach them with a slinky, you could pick that thing up and you can move it around. You could get those things moving a lot. Now, if you attached 2 nice like 5-pound weights or 10-pound weights to the end of your slinky, you're going to have a lot more trouble. If you did pick it up and the slinky didn't break, unless you're really strong, right, you're kind of limited in how fast you can get that kind of vibrating. So essentially what that does is create different sort of base energy states. So when you add that heavy isotope into a bond or a molecule, it will reduce the vibrational frequency. So that's kind of the basis of all mass-dependent stable isotope fractionation. And what that does in terms of this framework is it actually lowers your 0-point energy, right? And if we're thinking about equilibrium, that matters a lot because things want to go kind of get into that lowest energy state. And what really matters in terms of driving your fractionation and which direction different reactions are going to go and where the isotopes are going to go is how much of an energetic benefit you actually get when you stuff that heavy isotope into a molecule. And we can see that in a couple of different ways. So if you took 2 really sort of conceptual energy wells here, we can kind of think about the effect of mass on your vibrational frequency. So we can reduce this down, this kind of full form. We can think about energy. If you go into that 0 state, right, you're going to reduce that by saying your 0-point energy is going to be roughly proportional to your spring constant and your mass. We're using a funky notation for reduced mass here. And so essentially what you end up with, if you can imagine some kind of bond, a really strong bond, so maybe the example of phosphate and oxygen that Ruth was just talking about, something versus something with a weaker bond, when you substitute a heavy isotope into that system that makes a stronger bond, you get a much bigger energetic benefit than if it goes into this one with, say, a weaker bond. So right away, you can look at this and predict, all right, if I'm going to guess where my heavy oxygen 18 is going to go, and as a choice, it's going to go into that sort of bond setting because it gets a greater energetic benefit. OK, so the kind of rules of thumb here, if you have a higher K, you're going to have a higher 0-point energy. If you're going to have, if you're going to double the mass, so here we're both talking about doubling the mass, you're going to proportionally lower your 0-point energy, and so you can kind of see mathematically where these predictions actually come from. The end result is you end up with different delta E's. OK, and so this is where we've talked about a range of different things that when you come up, if you've taken a stable isotope class, and I'm not entirely sure what sort of versions of things they've talked about. This is one setting where you can basically say, OK, so one of your rules of thumb is that the heavy isotope is going to go preferentially into the chemical compound which the element is bound most strongly. So that goes way back to Beagleisen in 1965. OK, any questions on that? Yes?
Not a question on that, but does anyone have an extra packet? Jeremy doesn't have any. Yeah.
I think those are.
Thank you.
Thank you.
Here, I can.
Yes.
Yes.
Is always the case then, or is it just?
It's always the case. So this is not even talking about temperature. This is just your basis. When you think conceptually about whether you're talking about biological based fractionations, kinetic or equilibrium, this is kind of what underlies a lot of those mechanisms in terms of being able to predict where heavy isotopes ought to go. This is just basic foundation to give you a little bit of a conceptual framework.